This is 7.4, solving logarithmic equations. Right? So, general guidelines, if you're given something that has a log in it, so if you're given something in logarithmic form, we're going to do this. Okay, we're going to raise both sides to the power of the log space. If we are given something that is in exponential form, then we want to find a common exponent if possible, or if needed, and then we'll take the log base something of both sides, all right? Because up until this point, when you've been given exponential equations, it's been something really straightforward, right? Like 2 to the x equals 4 to the 5x, right? And so all you would do is you would just take 4, rewrite it so that it's 2 squared to the 5x, and then you'd set the exponents equal because you have a common base, okay? But what happens then if we have 10 to the x equals, I don't know, 9 to the x plus 4? Well, this is a problem because I can't rewrite 10 or 9 in a form that would allow them to have the same base. So here's where logs come in, okay? So if we're given a log, remember in the last video we talked about the swirly property of logs? So log base 3 of a number is basically saying 3 to what power equals that number. So 3 to the third power here, 3 to the third power equals x, equals our number. And what is 3 to the third? It's 27. Okay, so when you're given a log, we're going to raise both sides to the power of the log's base. So we walked through the swirly method, right? But basically what we're doing is we're raising both sides to the power of 3. If you say 3 to the power of log base 3, that equals like 1. Those like cancel each other out. So then you're just left with whatever that is. So this in general is true for logs. If I take 2 and I raise it to the power of log base 2 of y, then that 2 and the log and the exponent are going to cancel out, and then this y comes outside of the exponent, and it just is what we're equal to. Okay, it's something that we have to get used to. All right, here we have log base 1/2 of 3x plus 1 equals 2. So this is basically saying 1/2 to the second power equals 3x plus 1, right? So we're kind of raising everything, raising 1/2 to the power of both sides. Okay, so we end up with 3x plus 1 equals 1/2 to the second power. Okay, now we're going to just solve. 3x plus 1 equals 1/4. 3x equals negative 3/4. Divide both sides by 3. Right, and this is where some number sense comes into play. Negative 3/4 divided by 3 is the same thing as multiplying by 1/3. So we end up with negative 1/4 for x. All right, for something like this, again, we're going to raise both sides to the power of, well, we're going to raise x to the power of both sides, right? Because we're saying x squared equals 3, right? Some number squared is equal to 3, meaning if we take the square root of both sides, when we introduce the radical into the problem, we end up creating the possibility for a plus or minus. So x is equal to the positive or negative version of the square root of 3. Just to kind of tie some things together, if I say log base x of 3, where is that equal to y equals 2? Look at that, it's equal to 1.732. What's the square root of 3? Look at that, 1.732. Okay, so you might be wondering, well, Ms. Sotomayor, you said that negative square root of 3 was also an answer. You're right, I did say that. Okay, so then what's happening here? What's happening here? What's happening here? Okay. If I take log base negative square root of 3 of 3, and that's equal to 2, this is basically saying negative square root of 3 squared equals 3, which should be true, right? So why isn't our graph lining up? Great question. I'm actually just thinking through this right now. Right, I think it has to do with the way that this graph is jumping. Either way, I don't want us to get too lost in those details right now. If you told me positive or negative square root of 3, I would tell you that that's correct here. Okay, it has to do with the domain. Logs do not like negative values for x in the domain, so that's why that negative square root of 3 is getting taken out. But for now, just think about it like this. Okay. We're going to skip this example because it requires some log skills that we're not quite ready for yet. We'll see them in the next section. Okay, so let's see what happens when we are given something that's in exponential form. All right. So remember, go back to our guidelines. What do we do if we're given something in exponential form? We want to find common exponent bases. Okay, we want to find common exponent bases and then take the log of both sides. Okay. So 6 and 36, we should at this point be able to identify that we can rewrite so that they have common bases, right? Because 36 is the same thing as 6 squared. 6 squared raised to the power of 6x plus 3. Now we have 6 and 6. Okay, so this one's actually pretty straightforward. We can now set their exponents equal. X squared plus 10x minus 18 equals 12x plus 6. We're working with a quadratic, so we get to get everything on one side, set ourselves equal to 0, right? Because we have a quadratic, our methods for solving quadratics are factoring, quadratic formula, or completing the square. Okay, subtract 12x from both sides, subtract 6 from both sides. Let's see, oh, excuse me, this should be negative 2x. Okay. Now we're looking pretty good. Try to factor. We can factor into x minus 6, x plus 4. Meaning x equals 6, x equals negative 4. So we have two solutions here. All right, one more, then we will be done. I know there are a few more examples depending on what note packet you have, but this is going to be the last one that we look at. Okay. And let's try to rewrite our right side, because I notice that 27 is the same thing as 3 to the third power. And then we'll just carry on. Okay, x squared minus 16x minus 8 equals 12 minus 15x. We're going to solve quadratic again. X squared minus x minus 20 equals 0. Okay. Factor x minus 5, x plus 4, meaning x equals 5, and x equals negative 4. Okay, got two solutions. Those are it. We are going to stop there for today because the other methods for solving something like this requires us using some properties of logarithms that we're going to learn about in the next section. Okay, so we're going to press pause. We will come back to these two examples in the future if needed.